Chapter 31. This is entitled Faraday's Law. And section 1, Faraday's Law of induction, I like to call it, as seen elsewhere, electromagnetic induction. So before we get into that, I'm just going to take us on a journey that's going to lead us up to electromagnetic induction. So some notes here and story time. So before we talk about Faraday's law of induction, let's review, what we know about magnetic fields. Magnetic fields and forces. Okay, so we have that. So last time we discussed that a charged particle, a proton or an electron, that has a magnetic force on it is proportional to, the magnetic force that's produced is a cross product between the charge's speed and the magnetic field that it's traveling through. We discussed that a charged particle, proton or electron, positive or negative charge, and our symbol for magnetic force, this, defined by QV cross B. The magnetic force, the velocity, the magnetic field are all perpendicular to each other, three-dimensional. So this cross product between the velocity and the magnetic field produces this new vector, which is the magnetic force. So for example, we have magnetic field lines going like this, let's say, and let's say that we have a charge moving to the right at speed v. By the right-hand rule, our fingers will be pointing up, our thumb will be pointing to the right, so our palm is going to be facing out of the page. The direction of the magnetic force will be out of the page. It's headed towards you. So that means that this proton here is going to be shot in your direction. It's going to be in a circle though, because if this field is continuous three-dimensionally, it's just going to be shot out towards you and then wrap around in a circle. But in this instance, the magnetic force is out of the page. So likewise, we saw that the magnetic force on a current carrying wire is given by the magnetic field times the current through the wire times the length of the wire. For a current carrying wire. So that is if we move current through a wire, and you'll see why I emphasize the word move. We move current through a wire in a magnetic field. The wire produces, or not the wire produces, but it experiences a force. So, and that's what we saw yesterday. So just going down the journey before we get to Faraday's law. We took a look at Ampere's law, and we determined that the magnetic field around a current carrying wire is going to be proportional as 1 over R. That means that the magnetic field is going to get weaker the further away it is from the source of the current, which is it gets away, the further away it gets from the wire, the magnetic field drops. And that's given by mu naught I over 2 pi R. This is also the result of moving current through a wire to produce a magnetic field. So far, we've been moving currents through a wire against a force. This time we'll see that moving current through a wire produces a field. Mr. Faraday, as we're going to see, intuitively thought, well, uses intuition to wonder, what if I change, or what if I move a magnetic field? Can I get a current? It's kind of vice versa. So we will get there. So this is also the result of moving current through a wire to produce a magnetic field. So are you seeing the pattern? We need a moving charge or current to produce a magnetic field, or for that charge or current to experience a force. So first of all, so we've been moving charges and currents. Namely, we're going to flip things on its head and see, if I move a magnetic field, can I get a current? And vice versa, can I get a force and a charge? But we're going to be looking at the current case for the most part. So see the pattern. You need a moving charge or current to produce a magnetic field around that wire, or to have the wire or charge to experience a force. Moving charge, moving, something's moving. We're moving currents or charges. What if I move fields? Again, my illusion. Moving charge or current to produce a magnetic field, or to have a wire or charge to experience a force. Now, possibly taking cues from one Hans Christian Ørsted. So again, this is a story history of science, you know, kind of sort of thing, and physics here. Possibly taking cues from Hans Christian Ørsted, who was a high school teacher. And the work of Mr. Ampere. We'll get Ampere's law. In 1820, namely, that an electric current, a collection of moving charges, creates a magnetic field. Do this for short. Mr. Faraday comes on the scene roughly around 1830, I think. Faraday performs an experiment to see if a moving or changing magnetic field can produce a current through the opposite, or vice versa. Notes heavy, story heavy, but painting a picture. So what is his experiment? What does his experiment consist of? So what he does here, and I'll draw the picture, he wraps two wires to an iron ring. So one of the coils we call a primary coil, connected to a battery. And then we have a secondary coil okay, and secondary coil connected to an ammeter. Ammeters are devices that measure current because measure in amps. If I move a field through one of these wires, can I get a current? Current first, then we're going to see moving magnetic field creates a current. So the question becomes, why do this? Faraday, he knew that electromagnets are created when current carrying wires, when you have a wire with current running through, it's wrapped around metal, now that you can create a magnet, an electromagnet, or a magnet through electricity. So you get a piece of iron, you run current through it, you have a magnet. He knew this, and this was part of his idea for the experiment. So Faraday knew that electromagnets are created, and I've done that plenty of times in class. It's pretty cool. When current carrying wires, so they're wrapped around metal. So he knew that this electromagnets are created this way. So he theorized that this electromagnet could produce a current in the remaining wire. So I'll draw the setup here. So first of all, he's going to run current through part of the iron ring. We get magnetism, we get a magnet. How about if I run it in reverse? Take the electromagnet, have current run through it, or can that happen? That was his idea, his hypothesis. He believed it to be so. Current to produce magnetism. How about magnetism to produce current? That is his thesis. So again, electromagnets are created when current carrying wires are wrapped around metal. So he theorized, what if, or he hypothesized, AKA, so he hypothesized that this electromagnet could induce or create a current in the remaining wire. So he observed something. So here's the picture. I'll just draw this up now. So we have a battery here. And let me see. Put an iron ring there. And then we have, first of all, we have an open switch. So this here would be the primary coil I was talking about. Okay, I'm getting that again. So this is our primary coil. And then we have a secondary coil wrapped around here. And then this is going to be connected to an ammeter. So this ammeter, measuring current. So what he observed is, so here's our open switch. The first time that he performed the experiment, closed the switch here, and you notice a current, there's an ammeter, there's a current reading here in the ammeter, but then it goes to 0. So that's, pretty odd. So when he first connected the primary coil, he observed something amazing. The closed switch in the primary, this primary here, it registered a current in the secondary. So we have, current flowing through the secondary wire. And there was a readout on the ammeter, but then it quickly went to 0. And then when he opened the switch, we noticed an ammeter, let's say this read 3 amps the first time. Step 1, he reads 3 amps. And then the second time through, he opens the switch, he'll read -3 amps. And then it goes to 0. So he kept doing that, trying to, come up with some reason for it. But it was peculiar. Let me just finish writing this up. So the closed switch, we're closing this first time. In the primary, register current through the secondary. Now you can read it out on the ammeter. Then immediately return to 0. So it's like, okay, we have no more current flow, because I mean, we have a closed circuit, but why did it go to 0? So we have a steady field. So the readout was registering 0. So opening the switch, as I said earlier, it registered a negative reading, and then it went back to 0. Kind of a peculiar result there. So what we see here is that when Faraday ran current through the primary coil, you know, we got an instant readout, but then it went to 0 because now the current value it's now steady current value. So basically, what's going on is that originally there was no current. Now we connect this wire to the primary coil and we get current. So now we have a change from 0 to something. And then once that you know, you leave the switch closed, you won't get a change in the current. It's just going to be a steady flow, right? But then when you open the switch, we have a reversal. And in the first case, this current is creating a magnetic field that's, you know, and we can measure that current on the ammeter. But the second time through, that current or that magnetic field is going to register a current that's going in the opposite direction. So Faraday proved that you can create a current by a changing magnetic field, a changing or moving field. Like you can create a field by a moving current. So in the first case, again, we have current coming from the battery through the primary coil. We get magnetism. Magnetism through the secondary coil. Open the switch, that magnetic field that's still there in the secondary is going to cause the current to go in reverse. So we have field actually inducing current, even though the switch is open. So like you can create, so you can cause, you can create a magnetic field by, or you can create current by changing or moving field, like you can create a field by a moving current. So why is the field, or why is the current moving? Or why is the field moving in the case of Faraday? Because after you open the switch, that residual magnetic field in the secondary coil is still going to produce a current that goes in the opposite direction, because at the moment that you change the conditions, that is, open the switch, the magnetic field in the secondary is producing a current in the opposite direction. It's producing its own current by the way of changing the switch from being open or from being closed to open. You close it, current, through the primary, we get an electromagnet. Open the switch, the magnetic field then produces its own current, the same, in the opposite direction. And that, how do we know that? There was a current reading on the ammeter, even though the switch is open. Because, so that's kind of, counterintuitive. It could be because open switches, we've disconnected the battery. Why do I get a current reading? Weird, at least outside of Faraday. He's showing right there that something's going on with that secondary. The secondary coil has field. Something's creating that current in that ammeter. So it must be the created field, the field that was created in the first place when you close the switch. Current through wire, field, open switch, field producing current. Hypothesis proven. Ran it however many times, whatever. Comes with this law of induction that a changing magnetic field does produce current, as shown in this simple setup. But before we get to the conclusion of the matter, in order to understand this mathematically, let's re-examine, okay, the concept of flux. You guys remember magnetic flux a little bit from yesterday? I will reprise you. Re-examine flux, which, as we know, is similar to electric flux. Hey, 1 second. All right. Magnetic flux, magnetic field times area. Remember a little bit of that? Now, let's go back to the wire. Are you guys tracking that so far? You see what I'm saying here? Wire, primary, secondary, coil, ammeter, readout. That's what the close switch. Yep, readout. Now, open this guy. Does that make sense intuitively? Can you see what I'm talking about? You open this switch, we still get current, but it's like a negative. The current is now flowing in its opposite direction. Why? There is magnetic field that's going through this coil that's creating its own current in the opposite direction. Understand what I'm saying? Yes, no? Guys, you can feel free to speak. There's only 2 of you. Okay. Just want to make sure, because the visual is the most important thing, like absolutely. You can write down equations all day. But why are you doing that? Because you have a clear visual of what's going on. Okay, so magnetic flux, we know, is the amount of field going through this space. So remember, the wire, the current's going wound through the wire, but field is going along the ring. So there's there's a changing field. So before it was no field, and now we have field, and that's why we got a reading. The field changed, reading. It's now staying no change here, or it goes to 0. I think I made a misstatement just a little bit ago. As soon as this is closed, current stays closed, 0. Interesting. Open switch, -3. But a second or two, or however, very short time later, 0. Reason for it. So let's get into it. The amount of field, flux is the amount of field through an area. Okay, in a general case, I have, field going like this, and I have my displacement vector, my area vector like that. Then flux, generally speaking, is going to be BA cosine theta, because the cosine component is parallel to this part of the field. Well, the cosine part of the field is parallel to this dA, or integrated out to be A. All right, so this magnetic flux. So Faraday reasoned that the reason why the current goes from nothing to something and then back to nothing is because I'm changing the amount of flux that's going through in that instant. As soon as I hit the switch on, I get current. Leave it there, I get nothing. Because this flux is not changing after the first second. Open the switch, instant change, I get current going back the opposite direction. And the reason for it is because I'm changing the amount of magnetic flux going through this wire in a certain amount of time, very instantaneously. So current is set up between difference in potential, battery. So Faraday reasoned, I get a voltage. I can create a voltage by changing the magnetic flux through a wire. And I can change the magnetic flux by changing the field value, the shape of the ring, or even rotate it, because of my general equation for flux. Voila. Faraday's law of electromagnetic induction, at least that's the intuitive visual. And now let's write it mathematically. Voltage created, induced, Faraday's law of the induction, is the result of changing magnetic flux in a certain amount of time. So rate of change of flux. That's why in the instant, a time interval that's very small or large, whatever, some time interval, I'm changing the flux. It's a rate of change of magnetic flux to produce current, which comes from a difference in potential, which is my voltage there, this EMF. This is the 1800, so voltage is commonly written as EMF symbol. And then also the other experiments, I'm just now imagining. If I now increase the number of wires in the coils, now this is going to be a function of the number of wires. So the amount of voltage created is a function of the number of wires of coil multiplied by the rate of change of magnetic flux. Calculus language, d phi b over dt. That is Faraday's law of electromagnetic induction mathematically. So in terms of perspective, if the magnetic field is going left to right, the magnetic flux is positive, and then vice versa. So let me show that sentence more in a picture. One second as I draw that up. Let's do another experiment. And this is the one I've done in class for years. Had a magnet, and I had a, I didn't even have a coil of wire. I just ran a magnet through an ammeter. It wasn't connected, no wires at all. Just between the leads of an ammeter, you know, device that measures current, and that dial was going left and then right. As soon as I would move it in, it would go, let's say, to the right, and I move it out, it goes back to the left. So the current's going forward and backwards. It's changing, and I would go back and forth, and the dial is going left, right, left, right, left, right. Simple demonstration of inducing current. No wires in that experiment, no batteries. So now let's move a all right, let's move a magnet through a loop of wire with the north end first. Okay, so my picture is like this, north, south, and then my wires like that, and then I have field lines going through the wire and coming back. Not the best picture, but you know, go. So these field lines are going through the wire, you know, going all the way around. So, all right, before I get to that, the moving magnet causes a current to be read in the ammeter. Now, if I move the magnet away, the current reading is the opposite sign. Now, I've done it too, where I would move it in there and I would just let the magnet just sit. The ammeter goes to 0. Because I need I need the flux to change. I need to go in, out, I need to rotate it, I need to do something. It's always got to change. If you just have flux, you're not going to get current. No, steady. If you have just a steady flux, you won't get any current. Okay, so this is what happens there. If I hold the magnet still, nothing happens. If I move the magnet away, the current is opposite sign. Now we can use the right-hand rule to determine the direction of this current. In order for it to be, so let's say we have field going around the wire. And we're going to say that this is, you know, the direction of our field is to the left. And we can represent that by the thumb on our right hand. This time the field is just linear. Well, we can represent it as a line going through the wire. So our fingers are naturally curling up and then down. So the direction of the current in this case will be this way, up and over. Now move it away, the current just switches direction. Same value, you know, for the amount of field. It's gonna fluctuate as the field increases or decreases. Okay. Yep. Conclusions. Current can only be set up by a moving or changing magnetic flux, and the current, or the source of the voltage, or produced from this voltage, must be in a direction to create an opposing magnetic flux. So let me just write all that up because I'm bleeding too much in there. Current can only be set up by a moving or changing magnetic flux. not just field, because we're having an amount of field going through some surface area. Either it's going through a coil of wire, or in this case, the magnet is going through a wire itself, just one wire coil. Both cases are pretty much the same. Or we can have magnetic field curling around a current carrying wire. We're going to get the same thing. If we just increase or decrease the current, we're going to increase or decrease the flux or the magnetic field. But our job here is to see the reverse case of field producing current. So we're going to always have this flux, magnetic flux going through an area. So that's the most relevant example. Flux going through, and field going through some wire area. Yeah. Current can only be set up by moving or changing magnetic flux, and the current or source of EMF must be in a direction opposite. That's why I drew that incorrectly. Let me go back. Let me write this up and go back and change one small thing. So here we are. Conclusions. Current can only be set up by moving or changing magnetic flux, and the current or source of EMF must be in a direction to create an opposing magnetic flux. Faraday saw that you can create a current by a changing flux. This guy Lenz came around to say the current that's created is going to be in a direction such that the current creates its own flux to go against the original flux. I'll show that picture in a moment. To create an opposing magnetic flux, phi b, to resist the original flux. Now, back to my picture, my original picture here. Let me erase these guys. So what's meant by that is that if I move a magnet to the left, right, the current that's set up in this wire is going to be in a direction that will create a magnetic field to go against the original field. And the direction of that current will be pointing downward. Well, up from the back and then down. If you put your right hand up, curl your fingers toward you, where does your thumb point? To the left or right? You guys doing it? It's pointing to the right. So that's what that statement basically means. This current that's created by this changing flux is going to be in a direction such that the magnetic field created by this current is going to be moving opposite this original field. So let me say that again. The current that's created in this wire must be in a direction so that the field created by this wire, by this current, opposes the original field. So in order for that to happen, the current in this case must go up from the back and come, it must wrap around this way. And if we looked at, we turn things around, that would be in a direction that's counterclockwise. And then we just switch it around. So Faraday just had the basic idea, oh, there's current. But this guy, Lenz, I forget his first name, determined that the direction of the current matters. Or he determined the direction of the current in each case. In this case, the current must be, we'll say counterclockwise, such that the new or the opposing, the new opposing magnetic field or the induced field opposes the original field. So now we must make a slight change to Faraday's law. And I'm going to save some writing here. So E equals N delta phi B over delta T. Faraday's law, electromagnetic induction. Lenz came along and stated, okay, Faraday, I see you, but the current that gets created sets up a magnetic field or magnetic flux that opposes the original flux. That's what the minus sign here is all about. So when you put these two guys together, this is the incoming flux, if you will. And this is the created flux. So we have a situation where N phi B delta T is basically the changing original flux by the magnet is in opposition to the new flux. So that is going to equal 0. We basically have another conservation of energy relationship. Because remember, this is electric potential energy, potential difference. So the sum of the changes, so we can say, well, E original minus E induced is equal 0. So we have a conservation of energy, basically. So when we do this, obviously, it's a net result of 0. This results in a net of 0. The sum of the changes of magnetic flux, sum of the changes comes out to be nothing. Or you can just do it like this. It's the same. Well, it's being redundant. So the sum of the changes, I just want to rewrite this. I'll just be very glib about it. So this is the original, and then this will be the induced. Comes out to be nothing. We have conservation. And that should make some sense to you because in the beginning, before any magnet went through this wire, it was nothing to begin with. So we're preserving that case. The original flux meets an opposing flux, net of 0. And that's basically Faraday's law. And we're going to write it as basically this because that just basically states that whatever we're going to do with our original flux, the point is that the induced flux is always opposite the original. That's why the minus sign is always going to be a part of this law or this equation. I just wanted to take a little story on that. I mean, I won't do that for the other things, but wanted to do that. And then we will pause and do some examples. Okay, in section 31.2, we're going to be talking about motional EMF or voltage created by the movement of a wire through a magnetic field or a conductor, as we see here, this bar of wire here, this conducting bar. So we can get the voltage within this wire by, first of all, we can use the right-hand rule to determine the direction of this current through this wire. So for example, if this conductor here was moving to the right, as it is here, by right-hand rule, we can see that our fingers will represent the magnetic field, which is represented by the X's. The wire is moving to the right, which is our thumb, and the magnetic force on these charges, is going to be moving up this bar because our palm is going to be facing straight up. And so that's why the current is going to flow in this direction through this little wire and through the bar. Next thing that we know within this bar is that, let's see, as charges, let's see, so electric field is going to go this way. We're going to get the same amount of positive charges or protons accumulating towards the top as electrons accumulating towards the bottom. So we're going to get this region of, conventional current is going to be a flow of protons. So we're going to have this protons accumulating up top and electrons at the bottom. So as a result of that, we have an electric field in this wire that is the result of this formula here, as we saw back in chapter 30. So electric field is going to be the velocity of the bar times the magnetic field that's going through this little area. So again, this conducting bar is going through this region of magnetic field. Flux is changing because we're going to increase the amount of field as this bar goes to the right. So this electric field is going to be the electric field within the conductor. And from this perspective here, we're going to have the electric field pointing downward as the magnetic field points into the page. So if indeed this bar is moving at a constant velocity, then the magnetic force on this conductor is going to be equal and opposite the electric field or electric force on this conductor. We can determine the direction of the magnetic force on this wire by using the right-hand rule. So even though, so now the next thing we want to do is get the force on the bar. Right-hand rule, we have our fingers going into the page. Our thumb is going to represent the current. And so therefore, our palm is going to be facing to the left. And now, because that's what the with respect to the current that's going in this wire. So current is up, magnetic field is in, magnetic force will be to the left. So the magnetic force is to the left. That's just, dealing with the wire. We'll get back to the wire here. In a little bit. So this is what we have. We have the magnetic force on the wire pointing left as the current is going up through this bar. And our original force, whatever is causing this wire to go to the right, is going to be equal and opposite the magnetic force on the wire here. So it keeps it at a constant velocity. So in our configuration for equilibrium, to keep this guy going at a constant speed, the magnetic force, the induced magnetic force, must be equal and opposite whatever this original force is. That's what keeps it moving at V. Now let's go within the bar, because our point of this section is to figure out the voltage within the bar. What is the EMF or voltage created by this within the bar as the bar moves through this field? So whether we're looking at these positive charges here, the protons here, or the electrons, the speed of those charges, or the rate at which they accumulate at both ends, the force on either if you're looking at the electron or looking at the proton, the force on both of them is going to be an equal force set up by the magnetic force on these protons here, which is going to be exactly equal to the electric force on those protons. So in order for there to be balance, in order for those charges to move at the same speed, whether you're looking at proton or electron, the forces on them must be equal. And that's something that we saw earlier with this velocity selector back in chapter 30. So we get this guy, and so cross out the charges, and so we get the electric field is equal to V times B, which we were looking at here. Still within the wire, there's a voltage difference, there's difference of potential, positive to negative. We know by first principles that the voltage is equal to electric field times the distance being the length of the wire, the bar. And from this principle here, we know that that's going to be equal to B times L times V. And that's what's going on inside of the wire. That's the voltage within the wire. Yes, you know, we're not outside of it, we're just right inside. So this is corresponding to voltage inside wire or conductor. All right. Next thing, last thing here, we'll look at is what can we say about what's the relationship of this, the changing flux between this conductor and this field, because as it moves to the right, there's going to be more field coming in per area for over this area. So at this moment it's here, and then it's going to get even more magnetic field lines, and then it keeps on going. Let's say if, you know, if this wire is extended, as soon as this goes right, we're going to increase the amount of field here. So we're increasing magnetic field as the conductor goes right. We're not increasing the actually, we're increasing the amount of area as we go to the right, because the amount of field is going to be actually, we're increasing both. We're going to increase the amount of field and the area, because the space is going to get larger, and the amount of magnetic field lines will be increasing. So we are going to get a change in flux by increasing the area and the amount of field through that space. since that can happen, we know that we can get a voltage that is created by that moving bar, hence the motional EMF. So go back, so there's an EMF inside the bar, and then there's going to be an EMF or voltage created by that bar moving through this field. So we know that flux, magnetic flux, is magnetic field times area. The area that's created by the bar and the wire is going to be
Mr. Kelly, I'm
yeah.
sorry to interrupt. It's
Yes.
on the surface, right? Not at a distance.
What is on the surface? You mean this field?
Yeah.
Well, it's going through. It's a flux. So just pretend like it's going through this little wire, this wire that's going around like that with a resistor. Yeah. Going through it. So area is going to be, you know, side times side. So the length of the wire times the displacement. At least at this moment, we can, you know, play around with the, you know, changing distance or calculus of it and all that stuff. But at this moment, we know that the area is going to be side times side, length times not displacement, but the position at that moment. So we're going to area is length times x. So the magnetic flux through that space is going to be magnetic field times L times x. And so therefore we know that EMF is going to be negative n d phi b dt, and let's say n is just one and one wire. So we just say negative d phi b dt. And then that becomes negative d dt dlx equals negative bl dx dt. And then therefore, the EMF produced by this moving conductor is negative BL, and this is velocity, negative BLV. So essentially, the flux that's produced by this moving conductor is actually in opposite direction than the voltage produced within the conductor. Negative BLV. Which should, you know, make some sense to you, because before the bar actually entered this field and it started, you know, moving along that, you know, those two rails, as it were, there was no flux, or there was no voltage. So the voltage within the bar is going to be equal and opposite the voltage created by the bar moving through the field. So we have opposite flux or opposite voltage. It's basically maintaining the state that we had before. So you add this flux within the bar plus this induced flux by the motion. It's going to be equal to 0. That's the sum of the changes. So we're going to get BLV, and it's BLV equals 0. So that just stands to reason on first principles that if we get an induced voltage in one direction, it's going to be met by an equal and opposite one for conservation, to maintain the state of 0 that it had before anything took place. And so that's about it for the day. And let's say the current that's going to go through this circuit. So this is our new voltage. The current is going to be equal to voltage divided by resistance. We know that from Ohm's law. And since this is the induced voltage here, we can basically say that this is going to be the absolute value. Why is that? Because, well, conventionally we know current is going to be positive, but if we can have it move the opposite direction and current can be negative, doesn't really matter. But for our purposes, in what's conventional current, we're going to make the whole thing positive. So this is just going to be BLV divided by R. And so this is the voltage created in the entire circuit. And this is the current of that circuit. Any questions on that? Yeah, I do just find it interesting that we're looking at this bar, this conductor, and we're looking at the voltage within the conductor and the voltage within the entire circuit as this moves. So there's two ways of that a voltage is produced. This bar magnet coming through, charges are moving, positive charges accumulating here, negative, you have an electric field, and these charges are moving at a steady rate. And the current is going to be a constant around the circuit. So we determine that the voltage within that conductor is going to be given as BOV. That's the voltage inside. And then when we look at the voltage in the entire circuit, as this guy's moving through, not just in the bar, but with respect to this magnetic flux changing, we see that the voltage in the circuit is going to be opposite this. So again, as I said earlier, those voltages, as it were, opposite each other because they're trying to maintain the state of the system. The system in the beginning was no voltage. The voltages that get created as within the bar and within the circuit are going to be equal but opposite to maintain the zero that it was in the first place. So well, fascinating there. Any questions as we close up for today? So one last thing I want to say about this picture is that whatever this original force is, not important. We know that this induced magnetic force is going to be the result of charges moving up through this conductor. And then by the right-hand rule, we can determine that the magnetic force is going to be to the left, and it's going to be equal and opposite this original force to maintain this guy at constant speed. Very similar to what's going inside of the conductor. We have a voltage difference inside the conductor, and the voltage that's created by this conductor as it moves through this magnetic field is going to be an EMF that's opposing the voltage within this bar conductor here. So we have voltage going one direction inside the conductor, and as this guy moves through, there's going to be an induced EMF that's opposing the change inside. Again, to maintain the state of zero that it had in the beginning. So I just wanted to, talk a little bit more about these, this magnetic force here that's opposing this original force to keep this guy at a constant speed. I know I touched on it before, just Wanted to make sure that was cleared up there. But yep, we get equal and opposite inductions or induced voltages, which is the result of Faraday's law of induction. Whatever currents or whatever field we had in one direction is going to be opposed by field in the opposite direction. So for example, if, as this bar is going through this, this apparatus, the original field is inside. So we're going to have to get, current, this current that gets created that has this voltage from, let's say from top to bottom, voltage drop from high potential to low, then the induced voltage is going to be from low to high to have the voltages equal 0. And then the magnetic fields, or aka the magnetic flux, a change in the magnetic flux, they're going to equal 0 also, because the original field is going inside. The current is in such a direction that it creates a new magnetic field that comes out, that goes out of the page. So everything is maintained. We have the flux is constant, the voltage adds up to 0, the forces are equal and opposite. So this is a complete state of equilibrium from 3 perspectives. Voltage in the circuit, magnetic flux is constant, magnetic flux in is equal and opposite the created magnetic flux out, and the forces are equal and opposite. And that's it.